So in this section, we're going to talk about limits, which is a very fundamental part of calculus. So some fairly basic information here. We know we can find the value of a function defined by f of x equals x squared minus 4 over x minus 2 for f of 1. And you already know that means we just replace the x's with 1. And so when we have f of 1 and replace the x's with 1, we get an answer of 3. So what happens if we try to do the same thing, but instead of picking 1, we want to figure out what is the value of x or value of f of x when we have a number plugging in that is extremely close to 1. For example, let's say we have f of 1.1, just a little bit higher, f of 1.1. So if you do f of 1.1, you would have 1.1 squared minus 4 over 1.1 minus 2. And by doing the basic math on that, you get an answer of 3.1. So as we would expect, when we plug in a number close to 1 that's a little bit higher, we get an answer that's a little bit higher than the answer we got for f of 1. What if we picked a number that was a little bit less than 1, like 0.9? So if we did f of 0.9, that would be 0.9 squared minus 4 over 0.9 minus 2. And once you do the order of operations on that, you get an answer of about 2.9. So as we would expect that when we pick a number that's a little bit less than 1, we get an answer that's a little bit less than 3. So you can see in the chart at the bottom of the screen here that when we plug in numbers closer and closer to 1, we get answers that are closer and closer to 3. So like if we plug in 0.99, we get 2.99. If you plug in 0.9999, you get 2.9999, which is incredibly close to 3. And same thing on the other side. I mean, look when they plug in 1.0000001, I think I counted the zeros correct, we get 3.0000001 as an answer, which is incredibly close to 3. So you might be asking yourself, what's the point of this? Why wouldn't I just, if I wanted to figure out what I would get close to, why don't I just plug in 1 and that would tell me what the answer of f of 1 is? Okay, so let's take into account trying to find, same problem, but let's do f of 2. So if you do f of 2, that means you would have 2 squared minus 4 over 2 minus 2. 2 squared minus 4 would be 4 minus 4, which would be 0. And 2 minus 2, we already know equals 0. So we get 0 over 0, and we already know we can't have 0 in the bottom of a fraction. So this is why we need to discuss limits. Now, if you pick numbers that are close to 2, let me show you the chart that I accidentally showed a while ago. If you pick numbers that are close to 2, let's say we pick a number like 1.9, we get f of x will equal 3.9. If you pick a number very, very close to 2, like 1.9999, you get 3.9999. And on the other side, if we were a little bit larger than 2, 2.0000001, that gives you an answer of 4.0000001. So you can see that as we get closer to 2, the answer for f of x is getting closer to 4. But we can't figure that out by simply plugging in 2 in for x, because plugging 2 in for x gives us 0 in the denominator. And so again, this is why limits are necessary. So the notation for limits is the limit as x approaches 2 for whatever the function is equals 4. We can see that it is approaching 4. In the first example, we were plugging in numbers that were close to 1. So that would be the limit as x approaches 1 of that function, and that we found that that equals 3. So that's what the notation would be if you had the limit of approaching that number from both sides. We can also do what's called a one-sided limit. One-sided limit is you're trying to find the limit of a function as you approach it from one side. Now, the limit as we approach from the left of f of 1, and the notation for that is f approaches 1, and then it has a little minus sign. That notation means that we're approaching 1 from the left side. In other words, those numbers like 0.099999, etc. So as we approach it from the left side, the answer was 3 because we did get like 2.99999. As we approach from the right side, in other words, when we were approaching 1 from numbers that were slightly larger than 1, like 1.000001, and I hope you get the idea. That notation is the limit as x approaches 1 from the right. And again, as we approached 1 from the right, it was still equal to 3. But then a two-sided limit does not have any plus or minus after the 1. And it didn't matter which side we approached from, we were always approaching 3. So a two-sided limit only exists is if you approach the one-sided limits approach the same number from both sides. It's got to approach the same number as x approaches a given number from either side for a two-sided limit. But a one-sided limit only has to approach from one side. So you can see here why the limit as x approaches 2, again, that notation would be the limit as x approaches 2 of the function f of x. And that function, I'll go ahead and write that in, was x squared minus 4 over x minus 2. The reason that limit exists and was approaching 4 is because x squared minus 4 over x minus 2 actually isn't simplified. We've known from the previous chapter you can simplify that if we factor the x squared minus 4 into x plus 2, x minus 2, and the x minus 2's would cancel, leaving us with just x plus 2, which means it is a linear equation with a y-intercept of 2 and a slope of 1. You can see the graph over here. That is a linear equation of a y-intercept of 2 with a slope of 1. But right here, 2, 3, 4, since we know that we can't have an x value of 2, you can see that there is a little tiny gap right here in the graph. So if we were to graph this on our own, we would be putting a hole there to show that x could not equal 2. Notice that that is directly above the x value of 2. So first thing we're going to do is we're going to practice finding limits. Find the limit of g of x where g of x equals x plus 4 over x minus 2. The first thing you do when you're trying to find a limit is see if you can find the limit by direct substitution. Can we just plug the 2 in for the x to get the limit? Very similar to the first one where we could have just plugged 1 in for x to find the limit. So if we do direct substitution, what we get is 2 squared plus 4 over 2 minus 2, which means we're going to get 0 in the denominator. And since we can't get 0 in the denominator, we can't figure this out by direct substitution. So right now we're just going to plug in numbers that are very, very close to 2, and I'm not going to spend the time doing the algebra for that in the video because you're a calculus student and hopefully you know how to do that by now. So we'll just look at these charts here. So notice that when we plug in 1.9, we get negative 76.1, and when you get closer to 2 from the left side, like 1.999, we get an actually large number, negative 79,996. When we approach from the right side, getting 2.1 there in black gives us 804.01, and as we get closer to 2 from the right side, 2.0001 gives us 80,004. So notice that as we get closer to 2 from both sides of the equation, or both sides of the function, we actually don't approach the same number like we did on these two previous examples where we were approaching the same number from both sides. So we can see that from the graph that as we get closer on the left side, our answer keeps getting lower and lower and lower. And as we approach 2 from the right side, our answer keeps getting higher and higher and higher on this rational equation. So there is an answer to this, and I'm going to let the great mathematician Katie Heron from the movie Mean Girls explain to you what the answer of this would be.
All you can do in life is try to solve the problem in front of you.
The limit is -1.
Oh, crap. I lost.
That answer is incorrect. Now, we are in a sudden death. If Miss Heron can answer this problem correctly, we have a winner.
Limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh, God, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist.
Our new state champions, the North Shore Mathletes.
Yes, that's right. The answer to this question would be the limit does not exist. So if you've ever seen that movie and wanted to know what that means, that's what it means. It is approaching, as we get close to the target number, it is approaching two different numbers from opposite sides. Yes, that's right. The answer to this question would be the limit does not exist. So if you've ever seen that movie and wanted to know what that means, that's what it means. It is approaching, as we get close to the target number, it is approaching two different numbers from opposite sides. So while we do this, we're going to do this with a t-chart on their own. So we're just going to plug in some of our common numbers of, let's do 2, 1, 0, -1, -2. So when you plug in 2, you get the absolute value of 2 over 2. Absolute value of 2 is 2. And so 2 over 2 equals 1. And then when you plug in 1, you get the absolute value of 1 over 1. The absolute value of 1 is 1, and 1 over 1 equals 1 as well. When you try to plug in 0, you get the absolute value of 0 over 0. And so we can see we have an issue there that we can't have 0 in the denominator, so that's not possible. And then when you plug in -1, so when you plug in -1, you get -1 over -1. Absolute value of -1 is 1 over -1. Now that equals -1. And then when you plug in -2, you get -2, absolute value of -2 over -2. Absolute value of -2 is still +2, but the absolute value, or that's not the absolute value of -2, it's still -2, but it still gives us an answer of -1. If we were to plot all that into a graph, as you can see below, that's already been done, that's what the graph looks like. And there should actually, to make this more specific, there should actually be holes here and here, because it is not possible for the x equal to 0, so there's actually a hole that starts and ends each part of the graph. But you can see that as we are approaching 0, we're actually approaching different numbers from both sides of the equation because we couldn't do 0 in direct substitution. Therefore, this is another situation where
The limit does not exist. The limit does not exist.
And yes, she's right again. The limit does not exist.